Great. Hi everyone, and welcome to our first closure meetup by Health Samurai. I'm Vlad, and I'll be your host today. We are very glad to see so many closure enthusiasts here. Today's topic is Core Async Deep Dive session for those who want to better understand channels, goal blocks, and concurrency patterns in Clojure and other. So before we start, could you please drop in the chat where you're joining us from? It's always great to see how global our Clojure community is. And so a quick note, the session is in English. Please keep your mic muted unless you're asking a question. Feel free to use the chat to post question anytime. We'll collect them, and for the question and answer session part later, we will cover it. Now let me introduce our speaker, Andrei Listopadov, closure engineer at Health Samurai. So Andrei will help us dive deep into Core Async, exploring advanced patterns and real-world use cases. So please welcome Andrei. The stage is yours. You can start it. You're muted.
Yeah, I see. Yeah, thank you very much for the introduction. So, as mentioned, my name is Andrew. Today we'll be talking about asynchronous programming in Clojure, how it came to be, how it works, and we will look into some internals of Clojure Core Async. So, first, a bit about me. As mentioned, I'm a Clojure engineer at Health Samurai. I work in Clojure for the past 5.5 years, and in general, my experience is a little bit bigger than 10 years in profession, but I wasn't always a backend developer in Clojure. Previously, I worked in C as a bare metal programmer on system on chip like stuff, and it was exciting to switch from like bare metal programming to backend programming because as I later found, there are some common patterns here and there. Because of my switch to like backend programming, I came to learn about asynchronous programming and parallel programming, and at first I didn't really understand it, but then it clicked with me, and I actually realized that some of the asynchronous patterns are appearing in bare metal parts. So I think we'll touch this in this talk/discussion today. And I also have a general interest general interest in like languages and developing languages. I've made a few toy languages just as personal like education purpose. And I'm also helping developing the Fennel programming language, which is a small like Lisp-like language that compiles to Lua. It will be relevant in this talk again because I will touch some parts of Clojure Core Async that make it like portable, and we will discuss a little bit of Fennel a bit later. So, as I mentioned, this talk will be about asynchronous programming. We will start with like my reasoning when and why you should do parallel programming, when you should do asynchronous programming, and touch like a brief history of async in Clojure. Then we will dive deep into like implementation of Core Async. I will begin with a little introduction for those who are unaware of what Clojure Core Async is. I hope there is no such people here because it's a really good library and you should try it. But if not, this will slowly build from the bottom up to the internals. We will discuss how Go threads are implemented, how channels are implemented, what timers are, what gotchas with timers you can experience when working with Core Async, and we will look into the scheduler that makes it all kind of possible. Also, we will discuss like portability, why it's portable, and problems that rise from the approach this library is implemented. So Um, Before we begin, I want to point out that if you have questions, you can interrupt me, like turn on your mic, ask your question. We will try to discuss your question as it goes. So though we shouldn't like stay for a long time on one question because I want to like cover of all of this in a reasonable time frame. But I will try to answer questions if you have any. If you don't want to like interrupt me, we can always discuss this later, but I'm fine with interruptions. So just keep it in mind. So, asynchronous programming. As I mentioned, I was a bare metal programmer before, and after switching to backend, I had to learn about asynchronous programming. And at first, I wasn't like sure why you would even need an system for like this kind of programming because you already have threads. When I was doing bare metal, there were no threads because I usually wrote small like drivers for components on the system on chip, like memory controllers, timers, and such. So, like, asynchronous programming kind of felt weird to me because, like, we have threads, they have a lot more like abilities than async, and why would you need it? So I began like learning about async. I studied a lot of languages and looked into how they handle asynchronous programming and came to this conclusion that asynchronous programming in a language either exists, like is supported from the by the runtime, or it's attached to a language by some means, which like results in some nuances you have to keep in your head when working with it. Such is, for example, in JVM, because in the early days of JVM, before the JDK 1.1, there were green threads developed by the green team, and they provided some form of like trading, but they were mostly cooperative. So it's not like they were proper threads. For some reason, they were not really good for like JVM people, so they dropped them in JDK 1.1 and onward, and we had probably nothing for asynchronous programming until JDK 21, where they introduced virtual threads, which again kind of allow us to write asynchronous code natively on the JVM. But other languages, they did not like stay in one place. They developed their own approaches for asynchronous programming. For example, in Erlang, there is actor model, and I know it's debatable if it's async or not, but we will not go into there here today. In Go, it's communicating sequential processes or CSP with channels and processes that communicate over these channels. In .NET, you have like async await. In Lua, it's coroutines, which is not truly like a system for asynchronous programming, but it's a building block and you can build upon and implement asynchronous systems. And other languages have like other approaches like generators in JavaScript and Python and such. So every language takes their own like approach with asynchronous programming depending on what their runtime is capable on. In Clojure, we have like parallelism and async right now. So we need like to understand when we should use one and another. And again, to me, it was kind of like strange to have two systems that mainly do like similar things. And I, for myself, decided that parallelism is like useful for compute task when we need to parallelize computation. So we need to do a lot of things in parallel. And async being a system where you can spawn tasks that like execute like kind of in the background, it can seem similar to parallelism. However, the key difference between parallelism and async is that asynchronous programming is cooperative in nature. So there are no like tasks that execute in parallel, like with parallelism, for instance. And parallelism is usually limited by the core count and the abilities of the uh, cores that we have, like, for example, if we do parallel programming on a CPU, we have a lot of cores and they can do a lot of stuff. But if we do in programming in the GPU, we have a lot more cores than the CPU, but their ability is a little less like exciting when we compare them to CPU. In async, we are not limited by core count because, again, we are not using cores if we talking about like proper asynchronous programming, but we are limited by the acceptable time of reaction to events because async is useful for mainly IO bound tasks. And it brings me back to the days when I was working with bare metal and devices directly. And we actually had a lot of asynchronous programming, but I just didn't know about it because we were issuing tasks to specific devices, like for example, a networking device or like a memory controller or a like storage controller, and they, after operating on the commands that we issued to them, they presented us with the results that we have to take from our side of our application. And it's basically what async does, but it wraps it in a more like approachable constructs in a language. In Clojure, there was like some form of asynchronous programming from the start. It's called an agent, and agents are, they can sort about like actors, except unlike actors that don't have a supervisor, they are a lot more transparent and generally they just store some data and we can send messages to modify this data. We don't need to send message to like take the state of the actor, like for example in Erlang on the Beam virtual machine, but we can issue tasks, they will be serialized, and after the queue is processed, the state of the agent will be changed. But again, agents are not a true asynchronous like system for Clojure, at least not in the sense of how we are interacting with the system, because agent use thread pools and therefore they can have limitations. Because of that, there were third-party alternatives provided by the community, for example, Manifold, which I am quite familiar with, and it's an event-driven library which uses callbacks to like structure your code into an asynchronous program that flows and uses like streams and almost like promises to communicate. Promessa implements async await, if I'm not mistaken, via the completable future in the JVM. So it's again platform dependent. And there are probably some others, but I never actually looked for any alternatives after I was familiarized with Clojure Core Async because it's just that great. And agents and all of these other systems, they have some problems. They may be common between these systems. They may be like specific. For example, for agents, we have to keep our tasks quite short because if we block an agent or if we block many agent, uh, or if we have tasks that execute longer than it takes for a new task to arrive into an agent, we can either exhaust their thread pool, so no more tasks will be like executed, and then our queues will start to grow and we can even cause an out of memory exception because we have issued so many tasks. There are like separate thread pools that we need to keep in mind. We have like really weird error handling. I've seen a lot of problems with agents and it was really hard to debug. I'm not saying that it's like really better in Clojure Core Async, but for me, it's easier to understand stack traces, for example, from Core Async than from agents. But the main issue of agents and all all other systems is that they can't be ported to all supported runtimes that Clojure supports because Clojure can run on JVM, it can also run on JavaScript. And for example, in agents, there is a thread pool, and JavaScript doesn't have any kind of thread pools in it. So we can't port agents as is. And because of that, if I'm not mistaken, ClojureScript doesn't have any kind of system like agents in it. So the developers of the language needed a more universal approach for like asynchronous programming, and they developed clojure.core.async. Um, it's CSP based, so we have again communicating sequential processes like in Go. We have platform independent asynchronous threads that are like implemented by this library. They're not using anything from JVM, almost nothing from JVM. And we have channels that again can be implemented on top of the language itself without needing any support from the platform. So we can do like asynchronous programming both on Clojure on JVM, we can do it in ClojureScript on .NET, and we can even port it to other unofficial runtimes that may have their own asynchronous facilities. Like for example, there is a port of Clojure to Erlang, which is called clojure. And even though Erlang already has actor system, we can still write our code as we would in JVM, for example, and it will still work if we have a port of this library to Clojure or any other port of Clojure. Now we begin like well talking about Clojure Core Async, so I will start with channels. And channels are like the main thing you will interact with in Clojure Core Async. So let's like get impersonal here. A channel is, you can think about it as a queue. So you can put stuff in it, you can take stuff from it. And this queue can be unbuffered or buffered, depending on your needs. If it's unbuffered, it supports back pressure. So when it's not able to accept any data, it will enable back pressure and will do something depending on the context you're working in. Or it can be buffered, and you can specify different buffering strategies like fixed buffer, which when full enables back pressure. We have sliding window, dropping buffer, and you can actually implement your own custom buffers that can do pretty much anything you can think of. I myself never had implemented a buffer because the provided from the library ones are usually cover my needs, but in some crazy like situations you can do it. So it's nice to be flexible here. And with the channel, you can, as I said, do pretty much basic operations like putting data in and getting data out of a channel. You can also do so with blocking calls, so it will block the thread we are currently running in if the channel is not ready to either accept or provide data. So let's see a small example. Here we are using blocking operations, and well, they will block our threads. So we shouldn't really be using them in asynchronous threads because again, blocking in asynchronous thread is not a good idea. So in this example, we have a channel, it's buffered because we are working with blocking operations, and we try to put a string health samurai into this channel. Because it's buffered, this call will not block because we have a buffer that will accept this message. And then in the next instruction, we just take this message out of the channel and print it into standard out. If this channel was not buffered, we will block on the first instruction, and the next instruction would never like execute because and unless someone else would unblock this channel but by issuing a take operation onto it. Sorry. With parking operations, which are asynchronous operations, we don't block anything because, well, we are in asynchronous now context. And unlike blocking operations, which can be used in like both threads and asynchronous threads, it's a compile time error if we try to use asynchronous operation outside of an asynchronous thread. And the library will simply won't allow you to compile your code if you're using asynchronous operations wrong. So again, the same example as before, but now we don't have a buffer in our channel because we are not doing any blocking operations with this channel. So we actually don't need to buffer it in this specific like case. And in the first thread, we are trying to take a value from a channel. However, because this channel does not contain anything right now, this Go thread will park and we will continue onward to our second asynchronous thread, which will put a value into this channel again asynchronously. and it will unpark the previous thread, which will print our message to the standard out. So this works in like an asynchronous way, as you would expect from an asynchronous system. Now, we understand what channels are, we understand what like operations they have, and we see Go threads. So let's look into threads and how are they made. But before that, a question. Was everything I talked about clear? Any questions so far?
Guys, you can unmute yourself and say it to Andrew directly.
Could you please repeat what you said about async being really similar to low-level programming, like reading from I/O devices, I think you said? I missed that part.
Yeah. So asynchronous programming usually means that we like dispatch some kind of task to a separate worker. This worker can be like a network device. For example, when we are working with sockets in JVM, sockets, they are actually devices on your like motherboard on your PC. And when you send a command to a socket, it will take on and do its work. It will communicate with like global network if you are talking to some other, for example, computer. And in async, we issue this call to socket, and after it's finished, it will tell our operating system that it's done. Here is the data from the socket. And our program can actually read this as it is available. In bare metal programming, it's pretty much the same because we are issuing some like instructions from the CPU to some other device on the motherboard. Except we don't have like asynchronous threads, we don't have channels, we need to do it all by hand, basically. So it's nice to have a system here that will do it for us. I'm not saying that this is always how it works. For example, in JVM, it may not be like that because, again, JVM can be implemented in such a way that it can't talk to a socket and then like receive data from it in an asynchronous way. But in general, this is how asynchronous program will work, and it's like the general approach. Unlike in parallel programming, when we have like a thread running on a core, and if we need to wait in it, we will put this thread to sleep, and our operating system is responsible for like maintaining thread count and switching between them.
Thank you.
Yeah. So asynchronous threads, and in Clojure Core Async, it's a, as I said, platform independent implementation. They are extremely lightweight. We can have a lot of them, and actually because of that, library afters suggests that we should like only use asynchronous threads when we actually need them. But in practice, I've seen a lot of people using a lot of asynchronous threads, even though they could use like the other component of this system, which is callbacks. So it's fast to create them. They are lightweight, so it's not that big of a deal, but you should like always keep that in mind. And what's important, threads behave as channels. And we already seen what channels can do. We can like wait on a channel or we can put to a channel. So it's nice to have asynchronous threads implemented as channels because we can wait on a thread by the same means that we can wait on a channel. And it like unlocks a whole lot of possibilities for this library. And it's kind of interesting that asynchronous threads, or Go threads, as I will refer to them from now on, are not threads at all, because Go is just a macro that transforms our code to behave like a thread, but it's not a thread in like a general sense. So we will look into how Go threads are implemented by working with this example. And in this example, we have two channels. They are, again, unbuffered, but we actually don't really care about it right now. And one Go thread in which we first try to take data from channel one Then we put it into a variable data and process this variable with a function foo, which will transform our data by some means. And then we put the result into channel 2. So it's the most simple example that I could think of that will produce an interesting expansion of this macro. So let's look into what this macro actually expands. And as you can see, there is a lot of code. And this is the core of Clojure core async. It's our asynchronous thread. It's a bit hard to read this as is, so I've took some time to annotate what's happening here, the important parts at least. And we will start by saying that this is a lot of stuff that is doing some work behind backs to make this work as an asynchronous thread. But in reality, it's not a thread, it's just a state machine. So the first thing we are doing here, we are creating a channel. As I mentioned, Go threads, they behave like channels. And it's not because they are made to support channels interface. Instead, we just always see a channel as the result of calling a go block because it will always return as a channel. And this channel will contain the final result from the final expression inside of our go block after it's complete. We will see how it's implemented a bit shortly. The next thing that happens here is that we get our thread binding frame, which is JVM specific. It is different between each runtime, but the general idea is not. So we have some bits that are runtime specific, but they are used sparingly. And by capturing these bindings, we make sure that our thread will behave like a thread on the JVM. Because next, what we are doing, we are creating a state machine. It's a simple function with two arities. The first one is used for initialization, and as you can see, it just creates an atomic reference array, which will simply hold a reference to this function and some other state needed for this state machine to work properly. And in the second arity, when we receive state, which is this atomic reference array, we already seeing the implementation of the state machine. Again, we are grabbing thread bindings before we run the state machine itself. We do it so because when we created the state machine, we just defined this function. And when this function was executed, the bindings of the thread could have changed. And in order for it to behave like a thread would, we need to restore the environment around this state machine. So that's what we are doing first and foremost inside of the try block. And then there is a core of our state machine, which is just a simple loop that reads the current state from this atomic reference array, and it simply jumps to the state that we are going to proceed to. In case when we just started this state machine, it will be state 1. If we completed the state 1, it will change to some other state, usually the next state, but it's not not a general rule because some state machines can have loops inside them that will go through some states inside this case block. And as you can see in the first state, we have a take call, which was transformed from this asynchronous take operation, but it's no longer an operation like angle question exclamation mark. Now it's take exclamation mark, and it accepts state for some reason, and it also accepts state as this atomic reference array, I mean, and it also accepts the next state it should switch to after it's complete, and the channel that we are working on. In the second state, we are seeing that we are getting a value from the state machine, which was stored in this take operation and put into this atomic reference array. We get it from it and pass it to foo. And as you can also notice, our code was kind of rewritten from from bottom up because we had data assigned to the value from the channel, but now we have data assigned from the value already from the function foo. And then this data is put to the channel 2 along with some state from the state machine, this atomic reference array again. The next state we need to switch to and the channel itself. So this is the essence of this state machine. In the final stage, we simply put the resulting expression, result of the last expression into the state machine, into the channel that was stored inside it. And this channel will have our data. And after that, we have some error handling and reasoning if we need to continue right now, or we should park our thread by simply stopping the execution of this state machine. Ooh. I know it's like a mess. It's really, really like intricate and maybe hard to understand, but I hope it will become a little bit clearer once we get back to channels a little bit later. So in essence, Go macro just compiles our code into a state machine using the inversion of control strategy. It rewrites our code from like back to front instead of front to back. And it's very reminiscent of a classic approach with generators that use yield as a mean to return from somewhere inside the generator's code and then continue from there when we call it next time. You can see generators in like languages like Python. If there are Emacs users in this conference call, you may know that Emacs actually has generators implemented pretty much in the same way as I shown you on the previous slide, but in Emacs Lisp.
Sorry, one small question. Can I?
Yeah.
So you mentioned this is like a state machine. So does this can the state machine go like when it's finished? Can it go back to the beginning, or does it just go forwards in one direction?
It depends. So, for example, if you have loops in your asynchronous code, like a go loop, for example, there can be like conditions that decide either we are going forward or we are jumping like to an earlier state. But again, it depends on how your code is organized. I have chosen a simple example because like loops are really hard to understand in the code, but it can like jump back and forth if needed.
I see. Thanks.
Yeah, and this put operation that we saw on the previous slide that is responsible for putting data into a channel, it doesn't just put data into a channel, unlike it seemed to do. Instead, it uses a channel method put, which actually accepts not only the channel we are working with, not only the data we are working with, but also it accepts a callback. And that's where the magic of this library happen in reality, because this callback, as you can see, it accepts a state, which is our atomic reference array that contains a closure to our state machine function. So in this callback, which will be used if the channel is not ready like to accept the data, this callback will be issued once the channel is ready. And in this callback, you can see that we take in the return value, which is like what the channel is supposed to be accepting right now. So it's a value. And it sets this like value into the state machine itself and then starts this state machine from the state we are currently in. And the state it needs to continue from is specified right here. So on the previous slide, we've seen that it's state free. So we should finish in this example. And this state is written into machine directly. If the channel was able to accept the data, this callback would not like happen at all. It will be dropped. And this function will return nothing. This value will be nil, and we will check if this value is not nil. We will recur. Sorry, I'm mistaken myself. It will be a value that channel actually accepted, and we will continue right from here where we were in the state machine. So we will go to the state tree immediately without any kind of parking. But if this function did not return anything, it means that it registered this callback and it returned nil, and we will need to park our state machine. So we will not go to the next iteration of this loop, and we will just exit this piece of code. I hope it was in some way understandable. For me, it's like clear because I spent a lot of time with this system when I was porting it to another language. But as I am explaining it, I can see it can be a bit difficult. So to make it a little less difficult, let's forget about all of this and go back to like why this works. And this works because library authors, they decided that while they can do it all with macro, instead they should like make it a little bit more general. And they created a library which is tools analyzer. This library can parse Clojure in like host agnostic way, and it can analyze the resulting AST, which is abstract syntax tree. It's written in Clojure, and it is what powers the Go macro. It analyzes all of your code. It knows where everything happens, where like function starts, where like expressions start and end, and where you can like how can you transform this into a state machine. So the real power of this library also is in this library that this library use. And channels are like a special thing here because without channels we couldn't do anything at all. And earlier I mentioned that channel is a queue, but actually it's three queues. It's a queue for put tasks, queue for take tasks, and a buffer for data, which is generally also a queue, but it's optional. So going back to our example, we can see how actually channels work, and I've prepared two diagrams here. So I hope this is where everything that was not clear on the slide with a lot of code will become a little bit clearer. When we want to put data into a channel, we check if this channel has a consumer in the take queue. This is the same consumer that we issued with this callback. So it's this kind of function that starts a state machine. And if it has a consumer in the take queue, we just pass the data to the callback, and this callback runs the state machine that was stored inside this channel. If it doesn't have a consumer in the take queue, we check if this channel is buffered. And if it's buffered and the buffer is able to accept, we just store data into the buffer, and that function that we're using to put data, it returned a symbol that will like tell the state machine to continue. So there is no parking happening here if we are working with a buffered channel. And if there is no buffer or it's not like able to accept, I'm not saying it's full because it can be full, but it still can accept data. But for example, if it enables back pressure, then we park this operation as a callback in the put queue of the channel. So everything is inside the callbacks, and these callbacks are inside the channels themselves. So there is no like other system than channels in here. And if you want to take a value from a channel, we check if it's buffered, because buffer usually means that when there are no consumers, data is going into a buffer, so we need to take data from the buffer first. And if it's buffered and the buffer is not empty, we read data from the buffer, and again, no parking happens. If it has a producer in the put queue, we execute this callback, and this callback again starts the producer's state machine. And once the producer is done, we have our data in this like operation and our state machine contains. And if there is no producer, we again park this whole Go thread as a callback inside the take queue of the channel. Oh, so that's the essence of how channels work and how state machines and channels interact with each other. Any questions?
So really all
Sorry.
you need is an array and okay, macros, arrays, and first class functions. That's all you need to implement them.
Yes, exactly.
Okay, that's pretty crazy, honestly.
Yeah. Well, as you may remember, there are some like runtime specific stuff like getting the thread bindings, but then again, the most things that you need are exactly as you said, like first class functions, recursion, and some like mutable data structure, and that's all.
Is it how you implemented it in Fennel as well?
Not quite. I cheated a bit and I used coroutines, but the rest of so there are no state machines, but coroutines themselves are stored as callbacks inside channels. So instead of state machines, I have coroutines, but that's the only difference.
Okay.
Yeah, Daniel?
I was going to ask what the implementation of parks itself is in the flowchart, but now as I read it, I realize it's just adding a first class function as a callback onto a queue.
Yes.
So
Exactly.
I guess I answered my own question, but okay. Sorry, this flowchart is actually extremely helpful for illustrating this idea. Thank you very much.
Yeah, I was kind of like going to show it, but I needed to like blast you first with a lot of information in the code so that it will be clearer. Yeah, but that's not all, because there are other kind of channels in this library. So there are also timers, and timers are kind of the same kind of channels, except they are closed after a set amount of time. And even though it's like a regular channel, and
Sorry,
you, yes,
sorry for interruption. When you talk about the channels on the slide, 2 slides before, one more, you said this buffer for data optional.
yes.
What is this about? I'm a little bit confused on that. This buffer for data optional, where this goes into pictures.
Yeah. So a channel can be buffered, it can be unbuffered. If it's buffered, it means that it has a third queue for data, which is this kind of buffer. And in these diagrams, it's what we check in case if we are putting it into a channel, we check if it has a consumer. And if not, we check if it has a buffer. And when we are taking, we first check if it has a buffer. And if not, we check if it has a producer.
Sorry, Andrew.
Yeah.
What happens if we have like multiple consumers registered on the put?
They are in a queue. So
Okay, the first one takes, yeah.
Yes. Any more questions? I'm
No,
serious.
thank you.
Feel free to ask if you have questions. Feel free to just interrupt me. It's fine. Okay. So timers. And timers are, as I said, they are just channels, but they are automatically closed after like a set period of time. And even though there are just channels and we can wait on them, we can try to put into them. And I actually not sure what will happen if we try to put into a timer. But there are some like interesting stuff about timers because timers are soft. Their resolution is limited to 10 milliseconds, which means that when you create a lot of timers in quick succession, if these timers have like the same amount of time they have to sleep before they closed, and they are created within the 10 millisecond interval from each other, they will use shared object between all of them. So you should never close a timer manually. It should always close by itself, because it can, when you're creating a timer, it can actually be like not yours. It can be created by someone else in another thread if you're talking about like multi-threaded program. So timers are cool because we can like use them in tandem with everything else in this library to like create operations that depend on some time. We can do stuff like waiting with a timeout. We can use them to make, for example, a pattern when we restrict operations until like some timeout happens. So like the bouncing, for instance. And it's really nice to have timers in asynchronous system, because we want to be able to sleep asynchronously. We don't want to actually sleep as a mean of a thread, because threads can sleep, but it means that we are like wasting a thread. When we are sleeping in asynchronous implementation, that we have no threads, there is no time wasted basically. So it's cool to have timers. And an example, again, with timer, we can create a timer inside the Go block, and we can use alts. It's an operation from clojure.core.async, which is like select. If you worked with sockets, you may know that select accepts some amount of sockets, and once any of these sockets is ready, it will return data from that socket or write data into that socket. So alts works almost exactly the same here. And what's interesting about alts and timers and this whole system is that if we try to implement alts in a naive way, we may want to do something like a loop in which we will go channel by channel and ask if this channel is ready or not. For example, if we have 10 channels, we go, hey, are you ready? No. The next one, are you ready? No. The next one, are you ready? Yes. And this is how we can implement this. But it's not a great way to do it, because if we are like going through every channel and some of them is ready, but it's already like behind our pointer in this array of channels, we will not receive it, and we will need to take a full loop around and find the channel that is ready. So it's not like a good approach. What alts does instead is amazing, in my opinion. Alts is like the bread and butter, the greatest function in clojure.core.async, because it simply issues a callback on every channel that you specify it with. And this callback is a special kind of callback. It knows when it was called. And once you call this callback, it marks itself as complete. And this library, it has like a notion of completeness of a callback. And if this callback is complete, any channel that have this callback will skip it. So we issue like a callback into as many channels as we want. And once someone somewhere interacts with some of these channels and puts like data into a channel, it will call this callback. So else has almost no performance impact, no matter how many channels you have in alts. And it's great. In this particular example, we have two channels. So both of these channels will receive the same callback, and this go block will be parked in this callback. So it's the same kind of callback as I shown earlier. This state machine will be in this callback. And we have a timeout channel and a regular channel. So what else does it like knows what channel's callback was called, so it returns the channel it was like received and the data from that channel, and we can like check if this channel was a timeout channel or not. So I will not go into like the cont expression here, but what's important here is that because it's just a callback and our timeout channel is closed automatically, when it's closed, it will automatically call this callback. So we don't actually need like a separate system to monitor these callbacks. We only need to monitor channels. And I honestly think that this just is an amazing design decision from the library authors. So we have timers. We have events like that happen after some period of time. We have channels, we have asynchronous threads. Do we need a scheduler for that? And in this library, there is a scheduler or event loop, if you would call it. And it's the thing that is platform dependent. In ClojureScript, it's implemented with google.async.nextTick. In Clojure, it uses a thread pool, and I'm not all that familiar with Clojure implementations, so I can show you how it works in ClojureScript. And in ClojureScript, it's just a simple stop the world loop that executes every next tick. It will process only a fixed amount of messages, either like less than this amount, but no more than this amount. So if you have like 30 messages, it will only process 30. It will not wait for the next 1000-ish messages. And it will automatically re-inquire itself if necessary. So for example, if we have a lot of messages to process, like say 2000 messages, after processing first batch of 1024 messages, this function will exit, let the runtime work a bit in a natural way, and then it will be executed again by the runtime and process the rest of the messages. There may be more messages by that time. So it is not a loop that runs all of the time. It only runs when it is requested, and that's actually another brilliant decision by this library's authors, because when you issue any kind of operation on a channel, this library checks if it needs to like set up a scheduler, at least in ClojureScript. So if it needs, it will simply inquire it and it will run sometime later. If it's not, it will do everything in the same thread as we discussed when you don't need any parking like of the asynchronous thread. And the frequency of this scheduler runs is determined by runtime. And what's interesting in this particular scheduler is that when I was porting this library to Fennel, where we don't have anything like next tick in JavaScript, for example, my scheduler is almost exactly the same as this one, except I'm using debug hooks to like wait for some amount of like machine instructions inside the Lua virtual machine. And after n instructions, it will run my scheduler. And everything else is exactly the same. So even the scheduler here is quite portable to other runtimes if you have some kind of a way to stop your runtime and switch it to the context of the scheduler. But do we need a scheduler? Because this question may seem strange since we established that we have timers. Timers probably require a scheduler to work, but in reality, it's not exactly like that because yes, scheduler will like monitor our threads and channels like timers. It will push threads that don't have any like outgoing dependencies into the rest of our program. So like a hanging thread. If we are on a system that has a thread pool, we can like increase our throughput. So scheduler is generally useful, but it's not like required. You can forego without it if you apply some restraints to your like system that you're working on. So if you are using a fully reactive approach, so all of the events happen when you try to like observe them. And if you have no other threads in the system, so it's like single threaded like runtime, like Lua, for example, you can go without scheduler. And I know this because my library works in this way if it doesn't have access to like these debug hooks and it can't like use the scheduler, it will work without it. There are some concerns that we need to be aware of, but it will work. And here is an example when we need and when we don't need a scheduler. So on the left side, we have a Go thread, which creates a timeout channel and immediately waits on it. If you don't have a scheduler, this Go thread will start. It's just a simple state machine. It will park on this timeout channel. It will store itself as a callback into the timeouts channel queue. And since we don't have any kind of scheduler, this code will never continue because timeout is just an object that stores the time, the system time it needs to be closed. So we need a scheduler to monitor this kind of timeout channel and execute its callbacks. But if you have some external consumers inside this Go thread, so for instance, here we have a channel that is external to our thread. And again, we are simply parking on a timeout channel. So we are a callback inside this timeout channel's queue. But then we continue into a next instruction in our main thread. And here we have a blocking operation. And because we have a single thread, as we established, and we are working in like reactive manner, we know that we will block this thread indefinitely. So we can like take the role of a scheduler inside this blocking code. And that's exactly what my library is doing. It just emulates a scheduler. It knows about timeout. It knows that as we are blocking this thread, we can actually sleep on the OS level, and then we can continue from it here as the callback is executed as normally. So the scheduler is not strictly required, but it's nice to have it because our events and our reaction time to events dependent on how good our scheduler is. So I've been talking about like Fennel and stuff here that I've ported this library. So let's talk portability. And I think it's really great that this library uses macros and like really basic stuff from the runtime, like first class functions, to implement everything here because we sure can port this either as like a Go macro on another runtime like Clojure on a different host language, but we can also use this as like a recipe for porting this as an approach without like implementing the Go macro itself. We can, as I did for Fennel, I've ported the logic behind state machines and how they are stored into queues in channels on completely different runtimes that doesn't have any kind of macros like Clojure does. So the portability is great both for Clojure implementations and for languages that are not Clojure at all. And because there are no dependencies on like platform specific threads, and we can manually schedule our tasks because again, we are not using any facility from the language itself. We are free to do this on pretty much any language. I can imagine implementing this in Emacs Lisp, like no problem. Even in C, it will not be like a huge deal to make. There will be some like nuances with callbacks because C doesn't have like closures, but it's doable. I mean, it's doable. But the system is not complete without channels because channels give us these points that we establish where our steps in the state machine will be. So by using channels, we basically decide upfront where all of the parking operations will park. And it's really great because in case of a Go macro, channel operations are like beacons that it can use to transform into state machine. And if we are not using like state machine approach, channel operations still like a clear visual indication for a programmer where this like operation will park. And unlike in something like Go, which can like behind your back insert parks into busy loops inside asynchronous threads, this system is like completely statically like determinable. And that's another cool part of this library because in my port to Fennel, I actually deduce if blocking operation will block indefinitely and throw it as an error because like we can trace all of the channels and their communications and figure out if this will never unblock the main thread. So it's great combination of state machines, Go macro, and channels that make this library amazing. But not everything is that amazing, actually. So there are problems, of course, because this approach, while cool, it has like some limitations. For instance, here is an example. This code looks like correct from like the idea point, because we have a function that has an asynchronous operation inside of it, and we call it inside of the asynchronous Go thread. However, because Go thread is simply a macro, all it sees is like left parenthesis, my async task, right parenthesis, and it doesn't know what my async task actually is. If it's a function, it can't transform this function because this function is like outside of the Go block. So from the point of view of this Go thread, there are no asynchronous operation here at all. And from the point of the library, we are trying to do an asynchronous operation outside of a Go thread. And this is a no-no. In Go or in Fennel, where I'm using the like platform specific primitive for asynchronous processing of tasks, there is no such problem because runtime helps us. This is completely like normal code that you can do in both Go and Fennel, but not in Clojure. And the same stuff happens when we try to apply our like patterns that we use in Clojure every day, but in asynchronous context. For example, if we want to map over a list of channels with the take operation, it's a compiler error because actually this operation is not like a function. It's not even a macro. It's just a syntax of the Go like macro. There exists a macro version of this operation, but its only purpose is to throw error at compile time, like in this example, because here it's a macro. Here it's a syntax, and here it's also a syntax. But then again, there are like constructs in the language that we can't even transform into a state machine. For example, map is lazy. How would you go about transforming a lazy sequence into a state machine? It's a really hard problem. So because of that, the implementers of Go decided that Go will stop transforming code on function boundaries. So again, from the point of view of this Go thread, there is no asynchronous operations here at all. And from the point of view of this operation, it's called outside of a Go block because it contained in a function that has no Go block within it. Again, in Fennel, because we don't use macros, because we use like platform specific coroutines, this is not a problem because this is just a function we can use to map, and we can yield across functions, and we can even do like lazy sequences if we want to. It's not that hard because we are not transforming anything into state machines. So that's pretty much it. I hope you can now see why Clojure Core is an amazing piece of technology, because the way it uses macros and state machines and channels, like it's amazing. It allows for a really robust asynchronous model for Clojure and other dialects, but of course it has some like problems. And there are nuances how you write code, but there also are nuances how you interact with the rest of the system, because again, this is slapped on top of JVM. It's not integrated with JVM. So for example, when JVM introduced virtual threads, there were a need to write wrappers around like asynchronous separation of core async and asynchronous virtual threads. Or like if you are using a HTTP client, which uses callbacks and uses these callbacks to like do stuff in an asynchronous way, like for example Clojure HTTP, the client library for HTTP. You again need to like write wrappers for that to work. And actually the README of Clojure Core Async, well, I guess not a README, but on the clojure.org, there is this section about Clojure Core Async, and there is an example how to write a wrapper with Clojure HTTP library that uses callbacks. So there are always some like trade-offs with this kind of approach. It would be great if like JVM had asynchronous programming from the start, and maybe because of that we wouldn't have core async as like this highly portable solution. But maybe even if JVM had asynchronous operations from the start, designers would still decide to make it as portable because again they care about other runtimes that Clojure supports. That's all. Thank you.
Thank you. Thank you so much, Andrei, for this deep dive into core async. We will now take some time for questions from the audience or discuss something. You can unmute yourself and ask it directly. Guys, do you have some questions?
Yes,
Yeah,
thank you,
a
Andrew.
question. So you said that it only like expands the syntax on function call boundaries, right?
All right.
So basically, you cannot have a macro inside of the Go that has the syntax, right?
Yeah. So, for example, like here, map, it is basically so not like map. For example, we have for, which is a list comprehension macro in like Clojure, and for actually expands to a function inside of it. So if you write go and for inside of it, it will not work because you can't like transform this, because for is also lazy and it's finicky. You always need to keep that in mind, that if you are using a macro inside of a Go block, it can be transformed as long as there are no like unsupported constructs like functions, for example. Anonymous functions, I mean.
I was gonna ask, like, if it's lazy, you cannot do it, then does mapv work? But I guess not.
mapp will not work as well because, again, if we like actually use mapp here and map, we can use mapv, for example, which is like not did you mean mapv? I said
Yes, I meant
map.
vector map.
I heard
Yeah.
map p, which is map parallel. Like, yeah, map v will not work because we have to wrap this in a function, and then again, Go will stop on function boundary. It will not see this asynchronous operation. Because of that, you have like facilities inside the library itself. It can support transducers on channels, so you don't need to write like your own maps. You can use transducers, and it's still like shareable between regular Clojure and asynchronous Clojure because transducers are highly composable.
Yeah. Okay, so if you need to generate syntax, you just wrap the whole Go and like
Yeah.
expand there. Yeah,
Yeah.
okay. Thanks.
On alt, Andrew.
Mhm.
If the channel has multiple consumers, again, does that mean we cannot rely on alts?
Okay, so here's how it works. If we have a consumer on the channel already, then yes, alts will issue a callback, but it will be the next in the queue. And so if we put something into the channel, it can like be taken before the callback issued by alts will execute. But then the next put will actually go into alts. And to slightly mitigate this issue, alts actually shuffles its channels and issues callbacks in like random order, so that you would have a bit more like less predictable, I would say, order in which operations will go. So Alt specifically tries to make it less expectable when the operations will run. So it's okay to have this kind of interaction as you describe.
All right, okay. Within these alts channels, they will have like a shared state or flag, so multiple channels will not call it specific callback, right? If
Right.
once, yeah, it's
Yeah.
called.
The callback itself has a state. Like, it's not the channels that have like some state. The callback itself, it basically when entered, it checks if it was already called. And,
Okay, nice,
yeah.
thanks.
It's like another mutable, like atomic reference.
Thank you. Maybe anyone else have some questions?
Okay, other question, Andrew.
Sure.
Have you tried already core async flow, and what can you say about it? So can you bet
No.
your new startup on it?
No, unfortunately, I had no time to actually try it, and I'm kind of waiting for a stable release, to be honest. So I was looking into it. I was hoping I would be able to include it in this kind of talk because it's really interesting as a concept, because they are like completely turning everything upside down with how you work with core async, with flow, like. So unfortunately, I'm not familiar with it, but I really want to like dive into it like further and maybe port it again to Fennel. So maybe next year.
All right, yeah. I was about to think if with this flow, should we care about all this stuff around CoreSync or not? Yeah.
I think like you should definitely care about core async because it's like an amazing tool under your tool belt. When you know that you are going to like do stuff and you need to do it in asynchronous way, and you know about all of these operations that core async provides, because again, this library has a lot of amazing stuff. Like you can create like subscriptions on topics. You can like create manifolds when you transform like linear set of data into like parallel execution and then back into linear. So this library, you should just go read every function that it has and remember about it, because like it's amazing when you know that you can use it, and it makes your life so much easier, except when it's not. Because of course there are like, it's not like bells and whistles, but there are problems sometimes. But async flow is really interesting, so I will dive into it later. Thank you.
Hello, Andrew. I have a question too. I am very new to this library, so what would be use cases that I mean that's not even Clojure related, but where you would use this kind of library, or where have you used it other than the use case you mentioned for implementing it in Fennel?
I in my practice, I had a server which was like implemented in Python, and I had to interact with it. And this server provided an interface like, it's not HTTP server, it's just plain text socket server. So I'm just opening a socket like plain text connection to it and sending data to it. Because of that, there are actually like very little solutions for JVM that can like have convenience provided by HTTP libraries, where you can like keep connection alive, you can like have a pool of connections and stuff. So I used Manifold actually to implement like a pool of socket connections and asynchronous operations around this pool of connections to sockets. But it was real messy, and after that, I tried to rewrite it in Clojure Core Async, and it was much clearer and a lot easier to reason about. So that's one of the use cases. Another is like I had a service that talked to a database, and I had to do a lot of like transformation of the data before it goes into the database. And then again, this library provides like functions to transform your sequential pipeline into a parallel pipeline and back to sequential after it is like done transforming the data, so you can slightly increase your throughput by like accepting messages as a series, like 1, 2, 3, 4 messages, and processing them in parallel, and then again putting them into database like this. So these were the main ways I used Core Async. And another use of Core Async was not in Clojure but in Fennel. I have implemented an HTTP client like from the ground up, except sockets. Sockets, I used a C library for sockets, but everything else like request parser, like response parser and encoder, like supporting chunked encoding streams and stuff was implemented with Core Async as a base for like asynchronous operations with the server that we are talking to. And in my testing, my client was like 2 times faster when issuing requests asynchronously, like at the same time, but asynchronously, than when you do it sequentially, because actually sockets can do work while you are like issue requests to multiple of them. So I think I've used it in on this kind of like communicating with another service like approach, but you can use it without any communications because again, you can create pipelines of data like transformations with channels, and you can reason about these channels. And that's maybe where flow comes in, but I'm not sure yet.
Okay, thank you very much.
Thank you.
And maybe last question, Andrew.
Uh,
How safe? Okay, can I ask? Yeah. How safe it will be if I put big amount of data into the channels?
So
how quickly it could be like cleared and
do you mean as a single message or like a ton of messages?
yeah, maybe a lot of messages, but like every of them, yeah, every single message is big enough, so how it will be like cleared easily or
So to my knowledge, the size of the data you send doesn't actually matter because it's not like moved or copied anywhere. It's just a reference passed. So um, you simply indicate this queue has a reference to your data. So the size of message shouldn't be a problem. And channels are quite performant. You can create millions of channels and they will work like together. And they are quite good because you can watch the talk by the author of this library when he like issues a million of channels, like code threads, I mean, in JavaScript runtime, and it still like manages to update everything at 60 frames per second. But if you have like a little amount of channels, each channel is still like as performant as basically as a function call because it's just a function call. So there are some overhead on top of this because it's a state machine. You need to like restore state, save state, and так далее. But to my knowledge, it's like negligible. You don't actually feel it. Yeah, we had a question from Anton and I think Richie.
Thank you, Andrew, for your talk. I have a question. Since virtual threads was introduced in Java, so could answer it before, much earlier. And what do you think? Could it simplify the implementation if using continuations? What do you think?
Well, continuations are very similar to coroutines in Lua, I would say. Like they are all like similar in a sense that like long jump in C, continuations, coroutines, they are doing pretty much like similar things. They can like traverse stack and restore stuff on the stack. So it will be real like easy to implement such system with continuations or like coroutines because that's how I made final version of it. So it will be easier, but then the portability of the system will like will be gone basically. So maybe if there were continuations, green threads, virtual threads in JVM, they would still do it as state machines. It's my reasoning.
Thank you. Thank you.
Yeah, Rich.
Hi, it's not much of a question, but more follow up to what your answer to the to those. I'm not sure if you pronounce your name correctly. When you're talking about the performance, I think it's you can't just throw in a lot of data to a channel, right? Because the channel, when you create a channel, there's no infinite size of the channel. The channel is always limited size.
Yeah.
So you have to take in consideration of your consumer and into your what's the consuming rate. Because if your producer putting data onto the channel much faster than consumer consumes, you're gonna run out of you're gonna have a blocking, right? So everything gonna pile up. So that's something you have to consider. So it's more of design problem than anything else.
Yeah, that's actually correct. Channels have like limits on each queue. For take and put queues, there is limit of 1024 messages. So if you're issuing like operations into a channel and there is no one on the other side that consumes them, after 1024 messages, there will be an exception. But I was answering like in the context if we have like equal amount of messages and like consumer rate of these messages. So like in the context of performance of this operation, not like in the general sense that you mentioned. But you are correct. It's always what you should keep in mind when working with channels, that you may need a buffer. This buffer may be big, and you always need to like see if you can consume messages faster than they arrive. That's also like applicable to agents, because they also have the same problems, because every time you have a queue, you have this problem. It's not like dependent on what kind of system we are working with. If there is a queue, like you have this problem. But thanks for this note. I saw another hand. I'm not sure whose it was.
I think it was Daniel. Yeah, Daniel, please.
Real quick, you mentioned there's a tiny bit of overhead in restoring and saving context. Is Tools Analyzer like the vehicle that happens through? If I wanted to investigate that more, is that the library I'd take a look at?
I mean, Tools Analyzer is responsible for like understanding how can we compile this this code.
Okay, so forget Tools
code.
Analyzer. Forget Tools Analyzer. What I'm curious about is you mentioned that like particularly get thread binding frame there. I noticed that's from clojure lang var, but is that the method by which the state is saved and restored?
Yes.
Okay.
This atomic reference array is like your main storage of the state. The speed of this atomic array, how fast you can like set an index inside of it, how fast you can read it, is the limiting factor, because other than that, it's just a function call with a loop, and the loops in Clojure are quite fast. So there is also like this call, like reset thread binding frames, and now this is also JVM dependent on how performant you can do it. So you can't really like, you can think of it as almost like a zero cost abstraction, because you probably can do better than that.
Okay. And why atomic reference array? Like, why not just use like a vector or something?
It's faster than a vector, because
okay, that's a reason.
yeah.
Yeah. Okay.
Yeah, thank you. So guys, anyone else? Maybe there some experienced guy who has
who will destroy me.
other experience with core.async and want to share their experience. Okay.
Yeah, I've had some
Rich,
experience with core async. I use it to kind of model a high performance computing algorithm, right? So explore the concurrency inside the data and the algorithm itself, and I was able to get a very decent amount of speed up out of it. Yeah, so that was a pretty good experience there for me.
Cool. Do you have it available anywhere?
Yeah, it's on my GitHub channel. So I mean page. So it was my dissertation for my dissertation project. If you're interested in, you can pin me. I can share to you. Yeah.
Yeah, you can post it in the chat. I think
Okay.
I'm
Yeah.
interested because I like emulating computers, because on my first job I was working on VMIPS emulator, which like emulated the MIPS architecture, and it was fun. So that's another passion of mine, like small computers.
Yeah, so it's not arc. Anyway, so yeah, it's a implementation of a particular image reconstruction algorithm. You can take a look at here.
Okay, thank you. Vlad, make sure to save all the links in the chat, because I'm not seeing the chat. So can you like send me?
Yeah.
Oh yeah. I mean, it is in the. Okay, you can see the chat. How do I send you? Oh,
No,
okay.
no,
There
no,
you
no.
go.
Vlad
Huh?
will take care of it.
Oh, okay.
It's
Yeah.
okay. Yeah.
I need 1 minute. Okay, Andrei, I'll do it some later. I think we can stop it. And that wraps up today's talk. Big thanks to Andrei for sharing their knowledge, and to all of you for joining and participating. We will share the recording and relevant material soon. So if you have some ideas for future talks or want to become a speaker yourself, please reach out. Our community is always open to new topics and contributors. So yeah, guys, thank you. Have a great day or evening wherever you are, and see you at the next Clojure meetup.
Yeah, my sincerest thanks to everyone, because it genuinely was amazing.